All right, welcome everyone. I appreciate you all for coming. My name is James Kress. I'm from the KAUST Visualization Core Lab. Welcome to everybody in the room, and welcome to those of you who are watching online live or watching our stream after the fact. So I'm not going to be presenting today, but I'm just going to do a quick introduction to the Visualization Core Lab for you. Our presenter is going to be Thomas Theussl. He's been in the Viz Lab for many, many years, recently retired, but we keep him on as a consultant because he has such good information on ParaView and everything else that he works on, so it's good to have him back. So he'll take the stage in just a second, but I wanted to talk about the KVL for those of you who may not know what we offer. Sorry, I can't move my mic, otherwise I can't be heard. So for those of you who don't know what we offer to KAUST and what we can offer to your research. So just a quick introduction. There's currently 5 of us in the KVL. Our lead, he works on information visualization. I focus on HPC, SciViz, and in situ visualization. We have an AR/VR specialist who also does SciViz, image segmentation, and VISO type stuff. And then we have 2 data scientists. So the 3 core services that we offer in the KVL: training and workshops, data visualization, and data science workflows, as well as facilities. But the main thing we focus on are, of course, our training and workshops and our scientific workflows. So we have 3 training workshop series that we do every semester. We have the scientific visualization series. You're in the 2nd workshop in that series this semester. I did the introduction to in situ last week, and we have Tom again in 2 days doing, well, Tom and I will present that one. It'll be on HPC for ParaView. And then we have Ronell in a week or 2 doing some AR/VR stuff, which should be very interesting. And then we have our data science workshop series. That's already over. And then AI tools and techniques is already over. But those are all available online, and I'll show you where those are in just a second. And then the main thing that we care about in the KVL really is our scientific workflows. So if you're working on HPC visualization, image segmentation, or 3D analysis, AR/VR, large-scale AI or data science, we can help you with those workflows. We can advise you with those workflows, however you need. If you need help from start to finish, we can do that. Help with a specific piece, we can help with small components as well. I'll show you some examples of our highlights in just a second too, to give you an idea of what we've done recently. So if you need more information on who we are, you can see all of our highlights, our other training info and everything. That's all available on our wiki. This is available outside of KAUST as well. wiki.viz.kaust.edu.sa. Check it out. We've got everything listed there. We try to keep that fairly updated. Next, the training and events. So these are all available on YouTube, at least 99% of them. So if you check out our YouTube channel, we're at KAUST Viz Lab. You'll see we're at 108 videos so far, soon to be 109 once this one's done. But we have everything listed on here for all of our past workshop series as well, for all of our data science, scientific visualization, and that sort of stuff. Like some of these AI videos do very well. 48,000 views on some of these, and 21,000 views in 12 days on one of these AI videos. So it's pretty cool. A lot of good stuff on there if you're interested. Check it out on YouTube. So then, oh, I'm lost where I was. I think we got last slide. So just to give you an idea of some of the past, more recent work projects we've worked on, here's a few of the highlights. So we have a few things up here on top. These are AR/VR stuff. So he's done some things where he's had a mobile AR application that they've taken to a conference to present some of their research to attendees, so they can have these I think that one was fossils or something being projected live into the auditorium so people could see them on their phones and see what their data looked like at the conference. I've done a number of things on in situ visualization. Tom and I have worked on weather visualization. You can see a cyclone down there. And then I've done other stuff on particle advection and that sort of thing. Tom's the real expert on particles and pathlines, which we'll see today. And then, of course, we've got stuff on AI as well. So they've done some things called color PCA. And so they were going through corals and color matching corals to a color scale, depending on their depth, where they were when they were taking pictures, all kinds of interesting stuff with color analysis with coral. So if you're interested in any of these things, or if you have any projects, please let us know. But without further ado, let's switch over to Tom and get started with the FlowViz portion of the day.
Yeah.
Not talk. There.
1, 2, 3. Perfect. Everybody hears me. I have to stand here, I guess. Thank you very much. So welcome everybody now to the actual workshop. I'm doing this on flow visualization workshop actually for the first time. So let me know in between afterwards, anytime, if it's interesting or what kind of things you would prefer. And please forgive me if I'm not completely straight on the first time I try to explain something. So for those people who want to follow here or online, I would recommend to install ParaView 6.1. Older versions will be fine, but there are some things different. So some things might not work for you if you use an older version, and it's open source. You can just download it. Actually, let me quickly show that. If you go to the download page of ParaView, it's the 6.1 is pre-selected anyway, and your operating system you're on should also be pre-selected. So you just have to download whichever version you prefer, so zip file or MSI, and I would actually recommend the MPI version. Usually you need the MPI. It doesn't hurt if you have it. It depends.
Some Windows installations don't have the libraries, so it won't work.
Especially on Windows. Yeah, I never use Windows. On Windows,
I usually don't.
Usually they don't.
Unless you know you.
Okay, so MPI is essentially if you do parallel things on clusters and have to communicate with different servers. If you don't do that, you can download the version without MPI. You would be fine. And on Windows, I would actually recommend MSI, but whatever you want. I just wanted to mention, because I'm using a MacBook, and on MacBooks the Intel version is pre-selected, but the MacBooks are actually the Silicon versions which you would need. So if you have a Mac, make sure you know which versions to download, because if you have the wrong one, it will work most of the time, but sometimes it might crash, at least in my experience. You got the workshop materials, the link sent by email before this workshop, I hope, so you can download these slides. There are not many of them anyway, because I'm going to do this as a hands-on workshop. I'm going to demonstrate most of the things directly, but you can have those few slides, and especially the data sets. If you want to follow, and you have not downloaded the dataset yet, please download from the web page this dataset, if you want to follow. This is the dataset we're going to use today. I downloaded it from a public repository. There are more similar datasets like that. And here I forgot to update the link. That's still the link from last year. So you better use that link here to download the dataset, okay? But we're essentially using a dataset from that repository. I just modified it slightly that the ParaView can load it easier, but I still have to show you a few things to actually load the dataset. The thing that it shows, I hope it's an interesting one. I think it's an interesting one. It shows a lot of interesting phenomena. Is this a 2D flow around two cylinders and around an edge, actually. So the flow, you see two example images on the lower part here. The flow comes in from the left. There's a small object here. There's a small object here. And then it starts swirling. It has to go around this edge. Vortices are forming here, and then behind this wake again. There are two examples only showing scalar textures, how that flow might look like. We're trying to do more flow visualization things like vector plots and stream and pathlines. The most important thing is that this is a highly time-dependent flow, so it changes over time, and this changes a lot when you want to visualize. We'll see that later on a lot. That's what I want to actually, the most important thing, what I want to show today, that certain things, if you've seen some introductory workshops I have done where I talked about basic flow visualization already, we're always about static flow only, meaning flow that does not change over time. There things are a bit easier, and if it changes over time, you have to be aware of certain things, and that's the tricky part, and that's what what I'm doing for the first time here now in these workshops, and what I want to show. Okay, so also some other interesting things about the data set is that it's an unstructured grid. It has been discretized in different time steps on different grids to adapt to the flow, which makes it computationally more interesting, but ParaView can handle all of that, and you can actually visualize the grid itself, which we'll also do afterwards. Okay, hope that is interesting. I hope I chose an interesting data set, but we're going to work with that one. So the goals for today is that, as I said, still an introductory course. We're just using standard flow visualization techniques that are available in ParaView out of the box. And I just have a few slides. I'll stop using slides in a minute and switch to the laptop and demonstrate the things. That's how this is going to work today. Okay. So if you want to follow, install everything. If you want to just sit in and watch it, perfect. So what is ParaView? It's just an open source visualization application which is available on all platforms, and it's pretty scalable and pretty complex, and I think capable of doing most of the visualization tasks these days. We're not going to doing this today, but maybe on Wednesday for the HPC Viz workshop that you can actually do distributed and large data set visualization with ParaView. I'm not going to need that today. And there is, although it's open source, there's a commercial maintenance company that supports it. That's Kitvia, and we have a maintenance contract with them. So if there's some special problems you have with ParaView, you can also contact us. Maybe we can help you with a very special problem. And the other reason that you want to use ParaView here at KAUST is because it's available. You have people who know a lot about ParaView. I'm not at KAUST anymore, but I'm reachable online. James can reach me anytime, and we can help you with people with problems in visualization with ParaView. It's available on all systems you have here, especially on IBEX and Shaheen if you use those for your simulations or your workflows. And if you have problems with using ParaView on IBEX or Shaheen, James is the perfect person to contact there. So as I said, it's a general purpose visualization tool. You have all kinds of applications and data sets from all kinds of domains areas where you can use ParaView. Most of them are scalar or vector visualization, which you see here. So for example, here you have some scalar value, maybe pressure or temperature around the tank. And here you have a flow around a Formula 1 racing car, I guess. But the other thing is the general, where the generalness comes in is it can visualize all kinds of phenomena from very small, this is on some kind of molecule, to normal size like the tank and the Formula 1 racing car, to large size like Earth simulations, Earth mantle convection, whatever, or even to cosmic simulations if you want to. Because the data you produce is essentially always the same. The visualization algorithms you use are the same. You can use ParaView for all of those. These are examples from the ParaView, official ParaView examples from their webpage. And just a quick thing so that you understand it a little bit better, ParaView itself is just a layer, a convenience layer, GUI layer on top of the visualization toolkit, VTK, which is just a programming library. So if you're a computer scientist, if you're programming things and you want to use this visualization algorithm statically in your code, you can use just VTK, link it to your code, and you can use these algorithms. If you want to use them with your mouse and load data, click around, then ParaView is that GUI that gives you the means to do this just by using, without programming anything essentially. And there are all kinds of things that ParaView does. You have Python command line tools that you can automate things. You have in situ visualization. Oops, couldn't press the button. A layer, but we're not use anything. All we're going to use is now this ParaView client that lets you just load data, play around with it, and visualize it. Just for you also to know that VTK shows up in all kinds of file names, that you understand that this is because ParaView is actually just wrapping around VTK, or actually building on top of VTK, which itself, of course, is building on all kinds of, but that's computer science stuff, probably not so important. The vector field techniques. These are the techniques we're going to look at today. It doesn't look very fancy yet. It will look fancier in ParaView, but there are essentially a few techniques that you can use and should use. These are arrow plots where you just put an arrow at each sample point, or where you have some data which shows direction of magnitude where your flow is going. And streamlines are the most common ones, which also work for static flows. So a streamline is essentially a line like you see here that is a line that the flow is actually tangent at each point, right? So it's essentially following flow, which means you see where it's going. The problem is it's not a good thing, and we will see that later to use in time-dependent flow, which we're going to use. There you will need pathlines, which are lines that integrate over time exactly with the flow. You can think about if you drop a particle in the flow and follow the path that the particle will take, that's why it's called pathlines. That's then a pathline. You see exactly where it's going. And it's different in Streamlines, we will see that later. And maybe for time-dependent things, the best thing to use is still particle animations. You put some particles in there and let them fly around and attack through the flow and see what is happening in your flow. And ParaView can do all of that for you, right? So that's what we're going to do today. If we have time, we're going to take a look at this special visualization technique, which is called line integral convolution LIC. Produces very fancy images, very nice, but is also more for static flows. I just include here because it's easy and maybe it's good to use every once in a while. That's the point where I switch to the demonstration. Do I have to do something now? Just takes a few seconds. My laptop locked. No, I did not. Okay. So if you start ParaView, if you want to follow along, you might want to do that. I have actually 6.1 here. I guess I have changed the color layout a little. That might look different than yours. Don't be alarmed. It should still look the same. One thing I always mention before I do this, when you use ParaView, if it looks different for you here, you have only 2 tabs here. I have split up my tabs into 4. This is, for me, it's more convenient. You can do it in the settings. You don't have to do it. If you don't do it, you just have the first 3 tabs beneath each other, right? So you have to scroll a little bit through the things to find them. Let's see how it works. If you have problems with that, we have a break. I can help you with setting it up like that or showing you exactly where things are in the other layout. To start with, the first problem you probably have is that you want to load your data. And I have, that's sometimes easy if ParaView supports it directly, but a lot of simulations output the data in a format where you have to do a few steps, and I'm going to show you some of them here. So if you press the open file button here, or go to, of course, file open, which I can do anymore because it's already open, but you can go there several ways. This button on the lower upper left, yes, my mouse pointer shows up. And then you go to the folder where you downloaded the data, which should be called Pipe Cylinder 2D. I have a few other versions here, don't worry about those. If you're on Windows, don't forget to unzip the file. ParaView will not show the zipped file here, and you will not find your data. So unzip it, you should have a folder like that. In that folder, you have about 3,000 files, which ParaView groups into 2 groups here. I can ungroup them or expand them here. So there are lots of files in there, which is for each time step. You have one file, or actually have 2 files for each time step, and we have 1,500 time steps. So there are 3,000 files in there in the 2 groups, because the simulation, the way the simulation was output here is that it outputs the component of the flow, and it's 2D flow only in a separate file. Not all simulations do that, but some do, and I wanted to show you how to handle that. So to load the data, you just select one group first, and then press OK. And then you should see something like that. Not much, but it shows up here. And if you have used ParaView before, been to the introductory workshops, you know you always have to hit apply to do something. We do that. Then we loaded the data set. Let's take a quick look at that. I can zoom in a little bit. The first thing you might notice if you have used ParaView before is that, that this here now changed to the number of time steps here. So the first thing you might want to check when you load your time series, that ParaView loaded it correctly, is that the right number of time steps shows up here. This is the number of actual time, so the number of essentially files, or the number of time steps you use. This does not mean it's the physical domain of time that you use. This might also be important. So for example, you are, okay, this specific data set simulates a flow in a time window of 0 to 15, okay, over 16 seconds, 15, 16 seconds. But it does 100 time steps per second. So we have 1,500 time steps. but the time is actually between 0 and 15. But since the data is only given in the file names, ParaView doesn't know anything about the time. It shows this should be the physical time. It's also between 0 and 1,500. So that might be a problem. Especially, it will be a problem for pathlines, which need the actual time that the phenomena took. So we have to tell ParaView that this is not the actual time. We actually have to scale the time to the right window. In this case, it's simple because we just divide by 100. And there's a special filter for doing that. So I'm usually, if you've used ParaView before, you know that you have your filters here, and then alphabetically you find all of them, right? Since I usually know what filter I want and what the name is, I just press on Mac, it's option space, and on Windows, I think it's control space. It should bring up that little dialog where you can just type in the filter you want, and it will just filter things and suggest those that fit whatever you typed in. And I know the one I want is temporal shift scale. I want to tell ParaView that we have to shift at scale. We don't have to shift in this case. The shift will be 0, but we have to scale the time because it's not the right time. If you hit that one, you get the filter here, and we can just scale by 0.01, meaning dividing by 100. Okay, that makes sense. Let me show you, and you hit apply. The thing that changed is that time now here, the physical time actually just goes from 0 to 15. Okay. If you don't do that, it will still work, but it will do something, but your things will be wrong. Pathlines will be out of your domain too fast because the errors are in time just too long. Okay. I have to do that for the second time step as well. If people are following and if you have problems, let me know, because I have to show it now again, once more again. If everybody is happy, I will just do it quickly. Otherwise, I can go through it again in detail. Because we actually have to load the second component of the vector field as well, the V component. Usually, components of a vector field are called U, V, W if it's 3D. It's just 2D here, so it's U and V. So we also load the V component and do the same thing here. We apply and shift it in time. Oops. Yes. It doesn't group it. Right. Then you have, is this 6.1? Yes, you unselected it. You have to press one of those buttons here.
Oh.
Okay. Okay. Where do I come? Okay. Your question. So if you open your data, ParaView actually, sometimes you might not, the ParaView groups file names automatically in terms of the number they have in them. It looks for the last number in the file name and assumes that's the number of the time step, and then it groups them. Sometimes that's not what you want, so you can turn this off. You just turn it off with this one, right? So if you press this button, they are not grouped. But if you want to group them, you want to press this button, then they're grouped again. I cancel that. Okay, and so now we've loaded the data. But the problem is we have them here on the lower upper left. You know that from ParaView, you see your data, your U components and your V components. I always say this, and I always do that. I look at the information. If my data is correct, I see it's an unstructured grid. It has 7,000 number of cells and 7,500 number of points, and we have 1,501 time steps. So that looks okay. Right. But the problem is, if you look now, what actually kind of variables you have in your data set. Here you have the V component, and here you have the U component. Actually, we should look at the temporal shift scale because that's the important one. And we want to combine them now to a vector field. ParaView has to know that this is a vector. We have to combine them. That's also a step you have to do quite often in ParaView, so that's what I want to show. In order to do that, you select both of them. Make sure it's the temporal shift scale, it's both of them. On Windows, I guess you can use Control to select different ones. On Mac, you use the command to select more than one things. And then, again, you could use the filter menu, but I just press Option space here, type in the filter name. It's called Append Attributes. This one, Append Attributes. And if you select that, there's not much you can do, actually nothing. You just hit Apply. And the difference now is that if you go to Information, you have now both U and V at the same time. And that's what we need because we want to work with both of them as a vector field. The problem is ParaView still does not know that these are and that's also often, for example, OpenFOAM, I think, outputs data often flow fields in just 2 or 3 scalar variables. And ParaView doesn't know that these are actually the components of a vector, right? Because they just write them to disk and ParaView can read it, but it looks like a scalar value to them, and it doesn't know that these are the components of the vector field. And here the same, since we loaded them from files, ParaView cannot know in the first place, these are the components of a vector field. But we know, and we have to tell ParaView now, this is the vector field, so we combine them now to the vector field. For that, the easiest thing to do is, and a very useful filter which you use ParaView a lot, you might get used to, is this calculator filter here, because it just lets you do lots of computations. And one of them is to actually combine variables to a vector. But this is now also where things are different at 6.1. If you're using an older version, this will not work. Unless someone complains, I'm just going to show the new way to do it. So what you want to do is you want to create a new vector field. You give it a name. The default name is result. I don't like that and then you will have lots of results. I give it a name for a vector field. What's a good name for a vector field? I call it vel for velocity, short, and I know what it means. You can give it, don't call it U or V because you already have that, right? Give it just some name. Vel is good. And then you want to say that U and V are the components of the vector field. So you just create a vector by starting with, can you see that? Is it big enough? I think it is, right? Starting a curly brace, say U is the first component, V is the second component. And the third component, since it's just a 3D flow, we set to 0. Okay, and make sure that the U and V are actually capitalized in our data set, but you can actually check you have your available variables here under scalars. You could even select them if you want, but for U and V it's easy to just type them in. And if you hit apply, if you did something wrong, a window will pop up and you have some cryptic error messages which you never tell what actually the problem is. But the problem usually is that you made some mistake in typing in the expression here, okay? But this is simple enough expression that should be fine. Curly brace U, comma V, comma 0. Curly brace closed. And now if you look to information, perfect. You see that we have now actually a third variable here, our velocity, vel. And there's no nice way in the later ParaView versions to see all of it, so I have to change the window size. But you see here, U and V were scalars. This shows the range of the values in the scalar value. And here you see you have 3 components. The first component is U. The range of this component is the same as U, because it is U. The range of the second component is the same as V, because it is V. And the second is 0, because we set it to 0. So we have a vector field now here. Okay. Actually, I wanted to show this here exactly. You see in the room, you see it on the side, the slides. That's not much on there, so that you know what I'm doing. I'm still at the first bullet point here. That's what I was doing. I want to show you how you load the data. I wanted to show you that you have to sometimes change your time. The ParaView knows the correct time, and then you have to append the attributes and use the calculator. Because I now want to quickly go to arrow plots, or let's make a break now and do with the rest later. Let's make a break now because we are half an hour, and let's make a quick break. I can go through here and see if you all loaded the data correctly, and then we can go starting visualizing it after break. 10 minutes break, 5 minutes break. Yes. Okay, welcome back now, everyone, also online. So I think we have settled the problem with loading the data here mostly and some other small things. Now we have loaded the data. Things should look similar like this for you. Now we want to visualize it. And what we're going to use is, first of all, the simplest thing. We've done that in the more basic workshops, arrow plots. And let me show you that. So if you remember, or do this for the first time, not just usually when you have a flow field, it's probably a good idea to just look at an arrow plot. It's the simplest one. It will always work, but it might not, show everything you need. But the way you do it in ParaView is the filter is called glyph. So you can either bring up the thingy, the dialog, and say glyph. It's here, just the glyph. Find it in the filters menu somewhere under alphabetically, blah blah blah. Or in this case, since it's often used, there's just a button here called, and the tooltip doesn't say glyphs, but it says generate glyphs that represent everything. So a glyph is a more general word for, well, it can be, it doesn't have to be an arrow essentially. You can use different kind of glyphs, the glyph shapes, whatever. Hit that one, right. So again, in ParaView, this little gear button here always toggles the advanced properties on and off. I usually have it on because I often use advanced properties. Sometimes it's more convenient to have it hidden because then you find things, important things, more quickly. Like this for now. So I've hidden the advanced properties. I only have a few things I can set. The most important is which kind of glyph type I want. We want arrows for now because we want to see what the flow looks like. We want to orient them with our flow. This now should be the array that you created just before by using the calculator, and it should actually be the only array available because we don't have any other flow, other vector arrays in our data. It does not show u and v here now anymore because they are scalar values, and you cannot use a vector plot on a scalar field. And then often you want to scale your arrows by something, and obviously ParaView assumes that you have a scalar field in your data that does that. I think that's actually more often not the case, so my default case here would be either no scale array or the array itself. The difference is, that's also a bit confusing, if you say no scale array, it will actually normalize the vectors. Then all the vectors will have the same length, and you see only the direction. If you want to see actually the magnitude of the vectors in their length, which is most intuitive in my opinion, you have to select the area itself, which means it will scale each arrow by its length. So it will have the correct length. That's scale by magnitude. It even says here, we could even scale by other components. I think that's the most basic way to visualize a vector field, is to plot an arrow at each position with its length. The only difficulty is that often, okay, let me start the other way. Here you can choose, the point is you have to choose where to put your arrows. And one way is to put it at all points. With this data, that actually works. Often this is very dangerous. If you have a large data set, especially 3D, and then you plot an arrow at each point, you have millions of arrows, and actually even ParaView usually crashes then. In this case, we can just try it. I think maybe ParaView crashes, then I have to redo everything, but it should work. Now let's just hit apply. Should. So there you go. Okay, does not look very exciting yet. The problem is that the overall scale is too large. It's probably difficult to set automatically, but I think ParaView could do a better job than what it does here. It's just much too large. So we have to make that a bit smaller. I'm not quite sure now which one will work, but that's already a bit better. I want it even smaller. It doesn't get smaller. Doesn't get smaller anymore. No, doesn't matter. Okay. Anyway, good enough for now. Now you had to hit apply. You're right. Damn it! Everything. I am teaching myself to use ParaView again. You don't have to always hit apply. I was but that's also why I like to separate them into these 4 panels, because whenever you are in the properties panels, you have to hit apply. If you are in one of the other 3 panels, you don't have to take effect immediately. And I thought I was in the display panel when I changed the length of the arrows, but I'm not. It's in the properties panel. I have to hit apply. Fair point. Thank you. But the thing we want to look at today here is the time dependence. We want to go to the next. We're going to look at our flow. This is just the first time step. We want to look at the flow at the different times and how it evolves over time. And for that, you have, so first of all, you could choose just a different time step here, either by the physical number that you know, or by the more abstract number in terms of its time step ordering. Or you can use these play buttons here. So you think that makes sense. This is play in reverse. You can even then play from the end to the beginning, or you go to the next time step, or you go to the very end. I just go to the next time step for now, because what you might see, or you don't see, can go one further. Right. It seems that, okay, first of all, it's not nice. The arrows are displayed in a weird color. Again, ParaView chooses to color the arrows by something useful. It chooses a scalar value array that's in the data set. We have the U component in the data set, so it colors the arrow by the U component, which might be interesting. In this case, it's not. I either say solid color to just see the arrows in white, or then you can choose whatever color you want. Or probably pretty useful is to color it by its magnitude, so that you have a redundant information here now. The length and the color give you the speed of the flow in this at this location. So the long arrows are red now. The smaller ones are blue. Overlap a little bit with the color map for the background. Okay, let's do that quickly. I don't like the color of the background of the domain. That's in the calculator. So this L-shaped or corner-shaped thing is my domain. It's that we use in the calculator, and it's also coloring the U, which is a completely useless information pane. Let's make that solid for now. Now let's also color it by its better velocity magnitude. Okay, so you see that. You see a little bit already, right? You see that you have at the corners for probably, I'm not quite sure, but obviously the flow speeds up around the corners and also around the objects. That seems to make sense. I can remove or move that thing somewhere else. Just drag it somewhere else. But one thing you might have noticed when you press this advanced buttons to the next time step is that the arrows changed. And you probably don't want that, right? But the reason here is we put them on every grid point. And as I said before, the grid here is different per time step. So it puts the arrows only at the grid points. And actually, as I said, we can visualize the grid points, and we do that. If you make sure you have the calculator selected here, go to display, or just select it over here, but let's do it in display, and select the surface with edges. That shows you actually the underlying grid. And you see here that let's turn off the glyphs for a second. With little icons on the left, are there for turning on and off just a display of some of your display modules. If you don't want to see the glyphs, I'm just seeing now my simulation grid, right? So you see that if I go back to the very beginning, it started with a rather fine grid all over the place. And then when it advanced, it got coarser and coarser because it realized, okay, there's not much going on in this area, so I can use a coarser grid, save computations, and then this evolves over time. It's actually pretty fun, in my opinion, pretty cool to watch by just hitting play. If you hit play, it will go through all your timestamps. If you hit that, you see by just the grid that you're using for the simulation, almost a little bit how the flow looks like, right? But this is really just visualizing the grid over time. And the problem is, so you can hit pause or stop here and go back to the beginning. Let me go back to the regular surface plot. So surface is always just display the geometry as it is. I want the surface for my actual data, and I color it by the velocity, and I turn back on the glyphs, and then I hit play. You see how the arrows are evolving over time, but you also see that they keep popping in and out because they are only on the grid points, right? So this is not. I think it's not a good way to visualize it, and it's not a very good way to visualize a vector plot anyway. And it slows down a lot because we are actually using a lot of arrows now around these objects and in the regions where we have more grid points. So you don't even see the arrows too much anymore. So I hit stop here. There's a quick way to fix that, and one thing I wanted, no, fixing is the wrong word, well, somewhat fix it, just not in the correct way. If I go back again, the problem is that the grid changes over time, which means your arrows are placed at different positions all the time. They keep popping around. That's not really very good. We can actually, let me turn them off. Or to be on the safe side, let's delete that quick to redo anyway. I delete out my glyphs again for now. Can redo them quickly. This is my data set, and it says here unstructured grid, and it changes over time. What I want to do is I'm going to resample it on a regular grid. A regular grid meaning it's fine enough that I capture all the things. And, regular grid just means Cartesian grid essentially. It's much easier in terms of computations. And in ParaView, the way you do that is resample to image. All right, here this resample to image. Make sure you have your calculator selected. And then you have to choose the number of sample points you want in X, Y, and Z direction. And for this, a good one, reasonable one, good enough. So here's a trade-off, right? You can use a very high resolution, but then you will generate a lot of data points and it will get very large and things will get very slow. If you choose a slower resolution, you will miss lots of features, of course. So I think a good one is 450 by 150 by 1, because in Z direction, we have only one layer, right? And if you hit apply there, the first thing is now it resampled the bounding box essentially of your domain. So this L-shaped thingy, it's not an L anyway, is now actually a rectangle. And the areas here, the deep blue, the dark blue ones, are actually 0. ParaView, there was nothing there. ParaView has to put something there, just put 0 there. So that's why they're blue. So there's a disadvantage. If you a geometry like this, but the advantage is, so if I go to, and if you do this resample to image, it also changes your representation to slice. There's a slight difference between slice and surface. I would go back to surface here. In this data set, it really doesn't matter that much. But when it's 3D, the slice will just show a slice through 3D. Since this is only 2D, slice and surface are essentially the same, except that you sometimes get the errors for some weird reasons if you do a slice in a 2D data set. So I go back to surface. Well, actually, I go back to surface with edges. So you see that for that, I have to zoom in now a little bit. But this is now our new grid, right? So it's a bit finer, but it's regular all over the place. And if I hit play, nothing changes anymore in the grid. The color changes, of course, because it evolves over time, but the grid is now static. It's resampled on a regular grid. And now you can actually use, I think it's a bit better way to use the glyphs to visualize the flow over time, which we're gonna do. So I change this back to surface and hit and add some glyphs again. But now I should not add glyphs at all points because they're just far too many, right? We're gonna distribute them randomly. I think the best one is the surface-based sampling. There's a slight difference. Since it's our 2D, our data is 2D, volume sampling makes no sense anyway. You won't get anything. You can choose this or this. It doesn't make much difference. There's a slightly different sampling strategy for that. Go ahead. Go ahead. But you still, yeah. So how to say that? It's difficult, of course. So simulation guys won't like that. If you're a simulation guy, you're not going to resample your grid, which you probably set up in a very smart way that things are computed. For visualization, it's often easier if the grid is regular, like here. But the resampling might introduce errors, of course, because you're interpolating then the point in your grid. And yeah, if it's too small, or if you have too large distances, you might miss things, whatever. You did not really, so in ParaView, you haven't lost anything. So the calculator one still has your irregular unstructured grid, and the resampled image has your resampled grid. So you can use now each whatever you want. They're different. Numerically, yes. So if you want to, I don't know, compute something from your vector field now, like integrate something over an area and get something, the resampling might have changed the values and introduced some errors. Sure. For visualization, the same is true, but it will not show. You will not see it, right? That much. That's what visualization is. You want to take a look at your data. You want to understand it better. If an arrow now points, 0.01 degrees somewhere else, you're not going to see that anyway. But that's what I'm saying. If you don't like resampling your grid, then just ignore this part. You might not want to do it. That's true. For visualizing, let me just quickly show you what the difference now is in the error plot. Quickly. So again, where was I? We should not, okay, we scale again by the velocity. We should not use all the points, but just sample with a few. I think 5,000 is still too much. Let's make 500 and hit apply. So now they look like that. They're still a bit too large. But this is now our what they look like. The coloring is again by U, which is horrible. We make them by V. Okay. Let me turn off the color this time in the surface. This is U again. I don't know why. The solid color. So you see it like that. And now if you hit play, the difference now is that each point can stay at the position it was all the time, right? Because the positions now are not changing anymore. They're always the same. And which means that you see the arrows in the place where they are moving, and they're not jumping around. So it's a slightly better visualization than we had before. But of course, we might have introduced errors by interpolating and resampling to different grids. That's true. But again, this is just for the visualization. And there are other problems with that visualization because you are not really, I think you're not really getting a good impression of what's going on over time. So we're going to try a few different things. Okay. Can everybody wants to do this and has done it, or is there a question? Problems? I will quickly go show you a different thing, which you might know from some more basic workshops if you've done them. We're going to do streamlines again. So the streamline is, okay, let's just quickly do it. To speed things up, streamlines also don't work with the unstructured grid very well, so I'm doing on the resampled grid now. Again, true, it might introduce some errors, but that's not a very good way to visualize it anyway, so we can just, that we have seen it, and then discard it and say, that's not the way to visualize a time-dependent flow field. But let's do it quickly, it's fast. I go to resample image, to my resampled image. I actually change the background now to the velocity magnitude. And right, I want to add the streamlines. If you found it before, again, you know there's this button here, integrate streamlines in a vector field. If you want to use the filter itself, it's called Stream Tracer. You wouldn't have to use this one, right? But you can just make sure you have your sample image, You can try it with the unstructured grid if you want to. Then you select calculator 1. I use it with that one and hit stream tracer. And the way that you create streamlines in ParaView in the flow field is that, okay, it's create streamlines, but you have to tell it where to start the streamlines, right? So you have to create some starting points. And for that, you have you have two options essentially, which are called seed types. You can either create a line or a point cloud. The point cloud is actually 3D, I think. So in this case, the line is pretty cool. And it actually is pretty cool the way it's just default is to from one edge of the data set to the other. In this case, that's actually pretty okay. So I'll leave it. No, but let's move it a bit. You can just move it by dragging it so that it's actually within the bounds all the time. You're not hitting the edge here. Oh, let's make it. I don't know. Doesn't matter. You're not going to use it that much anyway. Like this. And the resolution, so it will create 1,000 streamlines. That's what the resolution here says. Along that 1,000 seed points where it will start integrating a streamline along that line. 1,000 is much too much, in my opinion. We can try it. It would still work, but it's not too much. I make just 100. And that should somewhat. We can hit apply. So there's our streamlines now. So they look fine, but ParaView disabled the grid underneath it, because usually in 3D, for example, you want to see only the streamlines because they are 3D flying around. But in this 2D case, it makes little sense. So I turn on the resample the image again. I see them here. And then I also, because they are colored again by some weird, first of all, I've shown that a few times. In order not to, if you click around and move things, not to move the line anymore, you just disable it here. And it's no information anyway, the line, right? You just disable the show line. You just see the streamlines. Doesn't look exciting either yet. I would actually change the coloring now to solid color. And that's it. So for that vector field, it makes sense. These streamlines, first I can actually make the line width, I think, if I make it a bit larger. Yeah, whatever. Get a bit nicer. So again, streamlines are the lines that follow the flow, or that are tangent to the flow at each point. But in a time-dependent flow, that means for each time step separately. And that just does not make sense, in my opinion. You can argue maybe, but it doesn't really make a lot of sense to visualize time-dependent flow, because you might get the impression here that the flow is just going through this tube like this, right? Which is not the case. Just the first time step just looks like this. And you can now animate again this thing, and the streamlines will change. But I mean, you get something you get this kind of a vortex up behind the third, this corner, which is not completely wrong, but still, you also have the impression that the flow is moving towards the corner here, but that's just because the streamlines are being seeded at different points and they move from time step to time step. You know what I mean? The streamline is going with the flow in this direction, right? But here the streamlines are moving in this direction. So you might have the impression that the flow is going down into this corner, which is not the case. It's going like this along the streamlines. So this is not a good visualization. Streamlines don't work for time-dependent flow, okay? Although they look cool. I mean, this is pretty awesome, right? It looks beautiful, but it's just not showing what's going on over time in the flow. That's why, and okay, we are just at a third of our simulation time. I could watch that forever, but it will take too long until it's finished. We're done. So streamlines, there are cases where streamlines are good to use. If you have a static field, if you have a magnetic field, for example, streamlines are perfect. If you know that your flow will be static over time, I had a project with the guys from the desalination center. They were flowing water through the desalination membranes for days. So when you looked at it for a few hours in between, the flow was static. It was always the same. There it works. But for flow like that, streamlines don't work. So in this case, I'm actually going to delete the Streamlines. And I'm going to delete the glyphs. We're not going to use them anymore. So, yeah. Let's delete them. The first concept now we're actually using, which is really an algorithm now, or a technique that's really going for time-dependent flows, which are called pathlines. So pathlines, again, I've never done that before, but by the way, if you just use the velocity magnitude for coloring your background domain, you can hit play again and see already a little bit what's going on, just how the flow changes in speed over time. And a pathline would now be, you can imagine it, you throw a particle in here with little to no mass, just so that it's just being tracked by the flow, and you just plot its path over time, right? Like what it would be, how it would be attracted over time. ParaView can do that easily. It almost looks exactly the same as, let me go back to the first time step. It looks almost like this is the same like the stream tracer, but it's called actually a particle path. That's confusing a little bit. So we're going to look at the particle tracer in a second, but the particle tracer is actually for particle animations, where you then actually see the particles themselves being dragged around. But it's quite similar to the stream tracer, which shows a whole line. The particle path will show the whole line. So it shows the particle path for now. Okay, and now ParaView actually asks us to provide the sources. So we have to provide an input, which is the flow field, and we have to provide the starting points for the pathlines ourselves. So there is no built-in, like with the Streamlines, there were two built-in methods to provide these starting points. The path tracer does not, or the particle path filter does not provide any built-in methods to provide starting points. So we have to provide them ourselves, and this is actually one thing where ParaView is pretty cool, in my opinion. You can use any geometry you have as a starting point for your pathline. So, for example, if you compute you could select the highest velocity points in here, and then just use them as starting points for the pathlines, or whatever, wherever you get your points from. Since we're not going to compute anything complicated here now, I'm just creating a few points, and the easiest thing in ParaView is that you just create a geometric shape or something. And here again, a line is actually, I think, the most suitable one. Everything else doesn't make much sense. But we just create a line ourselves now, and since this flow actually goes from left to right, it probably makes sense to just position the line at this side, because now the particle paths will go in this direction, right? Okay, and here it's pretty conservative. It has a resolution of only 6. 6 is a bit too little, too small, in my opinion. Let's use. Let's make 50. Okay, let's try that. I'll try it. I'll hit apply, and nothing happens. Nothing happens because ParaView is computing the path line to that time step where you are. So we have to actually advance. I'm going step by step in the beginning. If you step, you're not seeing much. Okay. We're going to cut that later from the video. I have just created a line for now. I have not created any particle paths now. So yeah, that's what I was doing before. Particle path. We want to show a particle path, right? So we create that filter. Now we can select the input. That's why I selected the resample. No, I don't want to resample the image, because the particle path can work with the unstructured grid. So you don't have to resample anything here. You work with the unstructured grid, which was your calculator one, the original thing. So in principle, you can now delete the resample to image filter. We're not going to use it anymore, because everything I'm going to show now, I think, yes, can work with the unstructured grid directly. So I use the unstructured grid for as the input flow field, and as the seed source, we select the line. And then you don't have much anyway. Just make sure that the flow field is the correct one. We only have one, so it should be. Here you can tell ParaView a few things about your mesh. So in this case, we actually have to say it's different over each time step, because it is. But if the mesh was the same over all time steps, you can tell ParaView that, then it would be a bit faster. The result will be exactly the same, but it will be faster because it can speed up things. It doesn't have to compute certain things. But in our case, since the grid actually changes, we actually have to keep here with different. We hit apply. Right, and now you see that actually the line changed into small points, which you almost don't see anymore. So I'll try to make them larger. Yes. So you get to go to display. You can just increase the point size by whatever you want. Maybe 7 is okay. And then I hit play. Yes. And I stop it immediately. The point line was pointless, point size, because I'm creating lines. So I'm increasing the line width now. And that's what you see. And that's actually pretty cool. So ParaView created the particle path to that time step, whichever you select here, wherever you go. So I can go step by step. It will integrate more. I can hit play, and I can just see the way the path lines go. So you just imagine that you dropped a particle in here, and now you're following it, and just somehow look at what path it took, right? And you see that things here are already completely different than the streamline, because they're actually starting to swirl around and overlap each other, and just look completely different than streamline. But they show you more what's going on, right, over time. So as you see, this interesting, after that obstacle, they start then afterwards swirling around each other, but also not in that regular way that the streamlines usually show. And some of our particles even capture this thing here. Okay, and you wait or stop it at some point when you're happy. It's still at half of the size of the time domain. So I can stop it here if I manage to get in between a computation. If you just want to see the end result, by the way, you just jump to the end of the data of the time domain with this button, right? Then I can do that. And now it doesn't show anything anymore, but it's computing all the time steps and then shows you the result at the end. It'll take a few seconds to do that. Hopefully not too long, because I wanted to. No, it's done. So this is now after 15 seconds, when you drop 50 particles in here, what were the path of the particles? And you see the coloring is not very good here. Let me change that to solid. Yeah, solid is maybe also not a very good coloring strategy, because you cannot distinguish different particle paths. There's actually a pretty cool one, is first of all the particle ID. So you have but then it's probably better to disable the coloring in the background. So here now each particle got a different color, right? So you see the blue line is one, the dark blue line is one particle path, the red ones. The color map is probably not great. You might want to create one with more variations between the particle paths, but then you would see better what different particles do. But it already shows a few nice things, right? You see that the particles that start on top here, or the flow that starts on top here, actually just goes essentially through, and everything that moves from here starts swirling around at the end. So there's already some interesting things going on. What else did I want to show here? What's on the... I again forgot to advance my slides here. Yes. That's essentially what I wanted to show here. So that's how you create particle paths. Again, the most important thing, if you have time-dependent flow, that's the right thing to use and not the streamlines. Streamlines look nice. Someone might say, "Ooh, it looks horrible. The streamlines look much nicer. Let's use the streamlines in the paper." But then the reviewers might complain that this is not really showing what you're doing. So we might have to make more, or you might have to play around with where to place the particle, the starting points for your path lines, and these kind of things. There was another coloring which was nice. It also computed. You also have in the fields here. You have the particle age. So now we have the color map. Essentially, the integration time, the time where the particle is. The blue is the start, red is at the end. Again, you see that the upper thing is going straight through and are out of the domain after, I don't know, 5 seconds or so. And then there are just a few particles that actually start swirling underneath that object over there, right? So by just playing around with these things, use different colorings, you can get a little bit of insight what's actually going on. And it's actually, I think, physically more meaningful to show this kind of things for a time-dependent flow than Streamlines. Streamlines just make sense. We're a bit ahead of time, but that's actually good. So I think we'll make a quick, no one is seeing me online. We should make a quick break, and we'll be back in 10 minutes and do the last part with the particle animations and some things then. Awesome. Perfect. Welcome back. So we have looked at this particle path, and we have 25 minutes left. I want to keep a few minutes at the end for discussions or questions. But I think that's good because we're going to look at something similar, but also very nice. And I think one of the most useful tools, but also difficult to do it right, is to do particle animations. In this case, so the techniques we have seen so far are good for as a visualization with a single image. So you can include them, for example, in a paper or on a poster or as one image. So there's a philosophy how to visualize time-dependent data. Some people think it's also valid viewpoint is that if you have time-dependent data, you should use time to visualize the data, meaning you should use animation. Fair point, if you can. These days, you have a laptop, you have your phone, a tablet, you can show the animations to everyone. So that's actually a good thing. 50 years ago, where people could just print their papers, they could not show any animations, right? But we can't do it these days, so it might make sense to just use animations. And that's what we're going to do now. We're going to create particle animations. For that, you can keep, again, I think you know that, but you can just disable the view here and don't see it anymore, or you can delete the whole thing and redo it afterwards. But we're not going to need them anymore. I'll just keep them because it's okay. The other thing I said, so instead of particle path, I said we have these two filters here, particle path and particle tracer. Particle tracer actually looks almost the same. So the particle path creates pathlines that we just had. The particle tracer creates particle. Blinking. Oh, there you go. Blink. Now where I removed it from my belt, I'm not gonna get it back on. There you go. Okay. Good enough. Perfect. It looks the same as the particle path. Again, you have to provide the seed source the seed points essentially for the points yourself. The good thing is we just created the line. We can try different things if you have time, but for now, probably not. You can play around yourself. You can try different geometric shapes, place them wherever you want to. You can try to use other filters of ParaView to extract certain points where you say, for example, you can compute the vorticity of your flow and start particles only at high vorticity regions, which might show you the swirling regions more clearly. Things like that. We keep it simple. We use some seeds we just provided. The input, again, can be the unstructured grid. The particles, the advection can work over any kind of grid. And the seed source, we use our line. And then go back to properties if you don't see the apply like I do. For now, let's keep it like that. Yes, again, the mesh is different over time, so we should use that. Force reinjection, we'll do that in a second because it's actually pretty cool. But for now, let's just keep it. You can compute the vorticity automatically if you need it, if you know what it is. We don't need it, so it doesn't take much time. So you can also compute it. Now let's compute it, and we have a nice field to visualize. And hit apply. That was a mistake I did. Yes, that was a mistake because I am on time step 1500. And now ParaView is computing all my particles up to time step 1500, and it will not stop before it's done. And we're not going to see anything because I have not really placed my points very cleverly. But that's okay. That's a learning curve. That's actually, yes, it happened to me 3 times while preparing this workshop. Now it of course happened here again. Always make sure when you do something that you are at the first time step, because ParaView will always compute everything back to the latest time step. But it's already done. It is. And as I said, we're not seeing anything. I'm not quite sure what's the reason. So although I said that a few times in the introductory workshops, if you do something and you don't see anything, there can be several reasons why that's the case. And one reason could be that for whatever reasons, there's even anything here to show. And you can check that in information. And that's actually the reason here. We have only one point. It might be somewhere, I'm not quite sure where it is, but only we injected 50 points, advected them all over the field, and only one of them survived. All the others went out on the right side. So nothing, but we're going to look at it now. So what I do is I hit the button to go to the very beginning. I should have done that before. And that's fast because ParaView doesn't have to compute anything. It's just setting everything back to 0. And then I have to make sure, because that's also what I forgot. So here, if I go to information now at the first time step, I see I have 51 points. That's makes sense because we put the line there as with a resolution 50, meaning 50 cells, so it created 51 points. Okay, great. But I don't see them. Again, next problem, obviously they are somewhere. Why don't I see them? How do I figure that out? First thing, I disable resample to image. I still don't see anything, so it could be that they are behind that geometry, for example, right? That's not the case. Now again, sorry, didn't get the question. I'm just showing. Fair point. It doesn't matter which. I could show the cut, but that doesn't change anything. I'm just showing the resample. Did I connect it to? But I connected it to a calculator, right? You're right. So we are working on the original data, which is this one. I was just showing that because it's essentially the same. That doesn't change anything. But that doesn't change why I'm not seeing it. What concerns me now why I'm not seeing anything. But you're right. I should use this calculator because that's the one I'm actually using. Why am I not seeing the points? The points are there. They are 51. Another thing you can do is try different display. The point Gaussian, whatever. Yeah, so they are there. Not quite sure but point Gaussian is not what I want to use. Just use points, then they disappear again. If I increase the point size, they still disappear. I'm not quite sure why this happens in ParaView. I think it is because the line has, the geometry is not specified in the correct way with connectivity that it can display the points, because it makes no sense, in my opinion, if I use point. So point Gaussian means it uses a kind of a Gaussian sphere to represent the point. Makes sense? And they show up here, right? I can somewhere change the radius. It's here to make them 3 times as large. They just get larger. It's nice. That's too large. But if I now change my representation to points, they are completely gone. That makes no sense, in my opinion. In my experience, it means that in the representation, the VTK representation, some connectivity, some cell information is not there. But there's nothing we can do about it in ParaView. One thing to fix it, if you don't want to use, let's try the point Gaussian. Why not? If I turn the calculator on, right, they're still there. That's good. So we can use them at least. Let's point Gaussian, but I want them a solid color again. They're white. So what I wanted to show you, what you should have seen when you hit play now again, these points just start. It's essentially the same as the stream tracer, with the difference, or the particle path, with the difference that you don't see the path anymore, but you just see the path. Okay. And the way I visualize it right now, it makes little sense because we had essentially the same information with a little bit, but we had almost the same information with the particle paths, and we would even see the path. So the problem here clearly is, and that's the biggest issue and biggest challenge in visualizing time-dependent flow, especially with particle animations, is where to put your particles that you vector, so that in the end you see something that shows the flow. And one easy way to fix this, so I can stop this again. This is good. I don't have to watch it to the end. One thing, especially for this kind of flow, because here, sometimes you have kind of different flows, but this one is nice because it goes from left to right. So you know that if you put your particles in here, they will go somewhere in this direction, right? But the problem was we only put particles there in the very first time step. So what we can do to make it somewhat a bit more interesting in this case is to actually re-inject particles at each time step at these original positions. Okay. So for example, if I do it at every 5th time step, you can put 1 in there, and you get a lot of points. But to visualize it and to show you what it means, I do it at every 5th time step. You see that it's not re-injecting. Why not? I did not apply. Yes, thank you. Did I mention that we always have to hit apply? Okay, now we can hit play again. There you go. Now every 5th time steps, it's again creating points at this position. At the beginning, this shows that looks a bit not very cool. But as soon as they start interacting there, it gets more interesting. Also, what I find interesting is that it's obviously following the speed of the flow in that. So the coloring at the background is the magnitude of the flow at that specific time step, right? That can also be a bit confusing. The points have been dropped in at some point and are just swirling around. But you see a bit better now what's going on, right? In my opinion. And you can watch this until the end. And you can play around with, I don't know, and re-inject more points. Use different places. Maybe since you know that there will a vortex or some things will swirl around there, place points there all the time. Things like that, right? So that you get the interesting parts of the flow. Okay, we don't have. It's actually I'm not that far ahead in time because I wanted to go quickly and show something else. There are hundreds of methods or things that you can do, and very advanced things. So this is just some of the simplest one, but it's already something that which gives you a first insight, even in the time-dependent thing, right? If you just go back and look, imagine what the Streamlines were showing. They never showed you this complete circular motion that you actually really get at the end, right? So because the Streamlines only show one time step, they don't show you the evolution over all time. You might want to take a look again yourself, convince yourself that Streamlines don't show what you want. What you want to do in the end then is, of course, you want to save this as a video, probably, because in this case, the dataset, I chose a dataset that is reasonably small, so we can do it in time. If your dataset is much larger, it might even take hours to generate every image, or I don't know. So in the end, eventually want to, let me quickly show you that. Although it's easy, of course, you want to save an animation. Done. You choose a location where you want to put it. You have to put the file name, test, so that you know in 2 years exactly what you did. And then you can choose a file format. I would recommend to actually save it as individual images. So for each rendered image, actually each time step you render the image, you save it as an image and then use a separate program to mount it into a video, because you're much more flexible. Then you can change certain parameters still. You can change the speed of the video. If you want to, if you save directly as an AVI, for example, that works for me, you say, okay, you have to set certain things, and then the video is fixed, right? And the video might take, in this case, it takes just a few minutes to render, but it might take a few hours to render. And then you figure out, I want it to be a bit faster. Then you have to completely render video another few hours, right? If you just save them as individual images, you can use FFmpeg or iMovie or I don't know, whatever program to put them into a video at the speed that you want. Just try that out. One thing is here, so since I actually rendered an AVI because I don't have any cool video mounting software on that laptop. If you want the video then to run at that speed that it's supposed to run, which means it should run for 15 seconds, right? Because that was our physically our simulation domain. But we have 1,500 time steps. If you leave everything like this, especially the frame rate at 1, the video will run for 1,500 seconds, which is much too long, much too slow. It's boring. So if you save the video and you want it to be at the correct speed, you have to set, in this case, the frame rate to 100, because we know I have 100 frames per second. Does it make sense? I hope so. But again, this is something you can play around. And you don't have to worry if you save them as images, because then you can always think afterwards when you have the images, what's the correct speed for the video. But if you just save the video directly, you better think about it now. If you have it, I did it before. Try it. It doesn't take that long, but it should look a bit like, I called it test.avi, obviously. Something like that. Then in the end, right, you can, there's some compression artifacts in the background. But then you see it's actually going pretty fast, right? But that's the physical speed that the simulation has. And the book done. And that's the next problem, right? I obviously set the compression rate in the AVI video production to something which created these artifacts. If I want to fix it, I have to recreate the whole video, right? If you have the images themselves, they are done, then you can use a program to create your video at whatever quality and speed that you want easily, because you have all the images ready. That makes sense? Okay. Everyone seeing that? Again, I did not advance the slides here. Okay. 7 minutes left. I want to leave a few minutes for questions. I'm going to show you quickly, because it's on the slides, that the LIC thing, some people like it a lot, some people don't like it at all. It's quick and easy, so I'm going to show it. Also, I'm not quite sure if it works on an unstructured grid. We're going to figure it out right now. It should, but I'm not sure. So LIC is, I'm going to show you. It's simple. You just go to display and you select Surface LIC. It's just there in ParaView, okay? And there it is. That's what it looks like. You can go to some properties and color mode, enhance contrast. Enhance the contrast a little so you see it a bit better. Let's go to a later time step. Something like that, okay? So what LIC does, it's essentially the same as Streamlines. It just takes a texture, a noisy texture, and that's why it's called line integral convolution, compute some kind of convolution along that line, which makes it appear that this noisy texture is being smeared along the flow, right? The advantage is that it's everywhere, that you automatically have a view of your flow, static flow everywhere. Where for the Streamlines, you remember you had to choose where to place them, and then they might be somewhere or not. LIC just shows you wherever it is. That's a big advantage. That's why a lot of people like it. You don't have to do anything. But there are several disadvantages. The biggest disadvantage is that it doesn't show the direction of the flow, right? It doesn't show is it going left or right here, which directions are those. By the way, Streamlines don't either, right? If you have a streamline, you don't know if the flow was going in this direction of the line or the other. So that's a big disadvantage. And again, it's also for static images. If you animate it, it looks cool, but doesn't really show you what's going on, right? Because it's again just showing. So you might have the impression from these things that you have a vortex here, one here, that are moving there, and in some sense there are, but they are not exactly where they look here, because it's the time snapshot does not really show you where things are actually swirling around, if they are swirling somewhere. Just wanted to show you that if you like it, you can use that by just turning it on. And you can fix a few things, for example, by adding the glyphs on top of it to show some direction. Of course, you can add the glyphs on top of it, scale them in the right size, and place them better, and so on to make. I use these kind of renderings in papers a lot. They look nice and people like them, but you have to use a few errors to make sure where they go. Otherwise, it's not the right technique for doing time-dependent flow. So the right techniques for you that we did today is either show pathlines or do particle animations. And I hope I have shown you all these things. Oh yeah, I wanted to show you how to create videos. We did, easy. I'll be here a few more minutes if you have questions. Those guys who are here, online people, there are a few, James mentioned them in the beginning. There are a few workshops still coming up. So you missed the first one, which was last week, but there will be 3 more coming up. Day after tomorrow, James and I will do one on HPC visualization. Focusing on the HPC part, there will be a basic introduction to ParaView. If you already know ParaView, that the ParaView part would not be interesting for you, but if you use ParaView on clusters and want to speed up computations or the visualization of your things, then you might want to look at that one. So if you're using, for example, IBEX, you have large simulations on IBEX and you want to visualize that, you might want to show up or talk to James. He's the expert on that. And we have our visualization drop-in, and tomorrow afternoon will be on the other side in Showcase, you know, where the big display wall is. We'll be there for 2 hours. You can just drop in and ask questions. But since I'm saying that for the people online, if they are somewhere in the region, because you guys who are here, you can, of course, just ask us now as long as they're here. Just catch us before we leave. And we have Ronel talking about augmented and virtual reality. He's doing great work, so you might want to look at that too. if you are interested in these kind of things. Otherwise, I think, thank you for watching online. We can stop the stream, right? And if you have any questions here, just let me know.